Welcome, fellow chemists, to a video which will calculate the number of your atoms which will decay while watching it. Since the clock is ticking on your atoms, let's get to it. Here is a banana, and to put that in proper scale, I have another banana. This simple fruit has become a symbol for radiation. In fact, it is such a symbol for exposure to radioactivity that there is an informal banana equivalent dose scale. Simply put, the consumption of a banana exposes us to about 1% of the typical background radiation that we live with every day. How does consuming a banana expose us to radiation? Because it contains potassium. Potassium is one of many elements essential to our diets, but not all of its atoms are the same. The vast majority of potassium atoms have a mass of 39. This number comes from the sum of protons, 19, and neutrons, 20, in the nucleus. The next most common is potassium 41, which has 2 additional neutrons in the nucleus. These so-called isotopes aren't very interesting unless you add up those percentages and realize it's just shy of 100. That leaves about 0.012% of potassium atoms unaccounted for, and this is where the potassium 40 isotopes, those with 21 neutrons, come in hot. Literally, they're radioactive. Also known as a radionuclide, this atom is unstable, meaning it will eventually decay into some new atom. Potassium 40 undergoes a process called beta decay, where a neutron turns into a proton, which remains in the nucleus, and an electron. Technically, the electron flies off somewhere, but I'm going to put it on the newly formed calcium 40. But we don't care about decay type or what the atoms turn into. Instead, we need to know how long this takes. Enter half-life. No one can tell you when a radionuclide will decay. However, as discovered by Ernest Rutherford of gold foil fame back in the early 1900s, it is possible to determine and thus predict how quickly half of a quantity will decay. If you were to graph your data, it would look something like this. Potassium 40's half-life is reasonably long at 1,248,000,000 years. It may be a bit ridiculous to say a time span in the billions of years is reasonably long, but here is the age of the universe rounded up to the nearest billion. One of the title holders for longest half-life belonged to Xenon 124. In 2019, it was observed decaying into tellurium 124. Analysis estimates its half-life is a mere 1.8 times 10 to the 22 years, which is nearly 1.5 trillion times longer than the current age of the universe. The current record belongs to tellurium 128. Its half-life is 2.2 times 10 to the 24 years, which is over 100 times that of Xenon's. But I don't have to worry about potassium 40's radioactivity, as those bananas are still sitting on the table. Unfortunately, the same cannot be said about the orange juice I had a few minutes ago. But the human body is composed of much more than just potassium. Though sources may vary on the specifics, these other 19 elements definitely play some sort of biological role, making them essential parts of our diets. There are an additional 9 that have a suspected role, and according to the Wikipedia page on this topic, about 36 more that are found in the body to some extent. While they may be there through some natural means, like they were absorbed from the soil by some plant that I ended up eating, I will consider these ones contaminants for simplicity. Now that I know the elements of interest, I can calculate how many atoms of these elements are in the body. Luckily, the same Wikipedia page has the data to get this calculation started. Adding the masses gives a value slightly less than 70 kilograms, so I added a bit to oxygen, carbon, and hydrogen to make it exactly 70. From here, calculating the number of atoms is pretty simple, and here are the extremes. The most common element is unsurprisingly hydrogen at 4.2 times 10 to the 27 atoms, and the rarest atom on the list is krypton with a mere 18 billion. Here are all the remaining values, and I will show you what I did with them, starting with oxygen. There are 3 isotopes, and oxygen-16 accounts for the vast majority of all of them. Most of the rest is oxygen-18, with an ever so slight amount of oxygen-17. Multiplying these percentages by the total number of oxygen atoms gives me the amounts of each isotope. Though in this case I've wasted my time because not one of these isotopes is radioactive. On the other hand, you might be saying I'm wasting your time because the oxygen-16 atom count is greater than the all oxygen isotopes count. That's because I rounded the numbers previously to the first decimal. Behind the scenes, where I push my Excel spreadsheet to the limit, the number of oxygen atoms looks more like this. Now back to how I'm really wasting your time to maximize the number of atoms decaying. Carbon is also composed of 3 isotopes, 12, 13, and 14. Based on the percentages, clearly I'm lying and carbon-14 is just a figment of my imagination. Except of course it isn't, because carbon dating, a form of radiometric dating, is very real and uses the very real and very radioactive carbon-14. Its abundance usually isn't expressed as a percentage, as there is an estimated 1.25 atoms of carbon-14 per 1 trillion atoms of carbon. We don't really care about the number of atoms of the other two isotopes, but a 70-kilogram body contains approximately 840 trillion atoms of radioactive carbon-14. When searching Wikipedia so I could do this calculation for the remaining elements, I found isotopes listed in tables like this. With 65 elements in all, I knew I needed to systematically reduce the number of isotopes going into the calculation. I kept any with the known abundance and removed those listed as synthetic. As for the trace isotopes, I checked the larger Wikipedia table or did a quick search to try to find an abundance. If I didn't find one, like I couldn't for argon-37 or 41, the isotope was removed. If I did, no matter how small, it was kept. Apparently argon-39 has a percent abundance of 8 times 10 to the negative 14. This method reduced 268 potential isotopes to the 33 you see on the screen now. Calcium-48 is the most common, with argon-39 the least, and most of them are what I previously called contaminants. In order to quantify how quickly your atoms are decaying, I need to bring back half-life. Though many of the half-lives of the remaining isotopes are in the millions of years or longer, the shortest belongs to tritium, H3, at just 12.3 years. The thing is, years is just too long a time span, and I need to change it to seconds for the calculation. That's a relatively simple fix, and it's about 389 million. The half-life equation you might be familiar with doesn't help us, as this would give us the number of atoms remaining after a specific number of half-lives passed. Instead, we need an equation which will tell us how many decay over a specific period of time. To get there, we need this half-life equation, which, despite looking much different, does work the same way, and it contains lambda. I will demonstrate how this is useful, but unfortunately it's in the exponent, so close your eyes if you want to avoid the algebra. Okay, you can open your eyes again. Depending on the unit of time we use for half-life, lambda, the decay constant, tells how many atoms will decay per that unit. Its behavior fits what we expect where atoms with long half-lives have small lambdas, so fewer atoms decay over that time period than for an atom with a shorter half-life. And now for the reason I've kept tritium on the screen the whole time. Inserting its half-life into the equation results in a decay constant of 1.78 times 10 to the negative 9. The actual number of atoms that decay in a given period is called the activity. Finding it is as simple as multiplying the decay constant by the number of atoms in the sample. According to my analysis, there are about 4,184,000,000 atoms of tritium in the body. Multiplying that by the decay constant means about 7 tritium atoms decay per second. Now let's look at all 33 isotopes. The isotopes can be organized into 6 groups which will be ranked from most decays to least. The first, which tritium is part of, are those that can be expected to have at least 1 decay per second. The other groups are those with at least 1 expected decay per minute, hour, day, and year. The final group is those with less than 1 expected decay per year. Since this video is lasting on the order of minutes, we can ignore the isotopes in the bottom 4 categories. For the remaining 10, here is their activity in decays per second. Potassium-40 and carbon-14 are the runaway leaders, and the final 3 are those with activities less than 1 on a per second scale. You can see that every second just over 7,700 atoms decay in your body. Now if I change it to per minute, we have all 10 isotopes contributing to the total, which is now over 462,000. I'm going to sync the numbers to the video length now. You might wonder why I bothered to keep those contaminants in this calculation. I don't know about you, but I know I've got potassium, carbon, hydrogen, and chlorine in me. But these other 6 are intriguing. All the other isotopes, even of the essential elements, really don't contribute anything on this timescale. In fact, calcium-48, the most common radioactive isotope in our bodies by a factor of 100, has an activity of less than 1 decay per day. Perhaps in the last 9 minutes and 20 seconds or so is exactly when one of those atoms decayed in your body. But the same can be said for many other atoms, so it's these 10 I will stick with. If you don't find those isotopes intriguing, or you guarantee your body is a contaminant-free wonderland, just reduce the total on the screen by a few thousand. Go bananas with your adjustments to the numbers. For example, my body mass is over 70 kilograms, so my personal number is larger than what's on the screen now. Editor Chemist here with my own value and possibly yours based on 10 minutes of decays. Although since the beginning of this video, over 4.5 million atoms have decayed in your body, and the number just keeps growing, so reducing it by a few thousand isn't going to do much. However, before you go and mourn the decay of millions of your atoms, this number represents a bit less than 7 times 10 to the negative 20% of all your atoms, which I think we can agree is rather small. Nevertheless, I thank you for sacrificing your atoms to watch this video. Until the next one is uploaded, I suggest replacing your lost atoms with a nice banana.